Yeah. Can we start? Huh? Not yet? Okay.
What? People will trickle a little bit more.
Yeah, okay, we can wait. How much time is there in it?
I think according to me, it is 3:31. Okay, yeah, okay, now that.
No, okay. Okay, all right. Now we can wait a couple of minutes, Jess. So maybe I can use this 3-4 minutes to introduce one of the to our guest. So good afternoon to all of you, and it is indeed great pleasure and honor for me to introduce Professor Christopher Scott, who is going to deliver a talk today on climate adaptation for resilient mountain water towers, insight and opportunities in Appalachians and Andes. So we are very fortunate to have him here. Professor Scott is a full professor and Goddard Chair at Department of Ecosystem Science and Management, and as well as he is the Director of America's Water Energy Food Nexus Alliance at Pennsylvania State University. He does most of the work in a transdisciplinary manner. He works on water energy food nexus and water security and transboundary water issues. These are really very important for us in this country because most of our rivers are transboundary rivers. And also there's a lot of work on water energy and food nexus needs to be done in this country for effective and proper management of water resources. He's also earlier, before joining Pennsylvania University, he was director of Udall Center for Studies in Public Policy and professor of geography in Arizona State University. So he is a very well-known professor in his field, and we had a wonderful discussions. We interacted earlier in Kathmandu, where both of us were visiting EC mode to work on cryosphere and hydrological issues in there. So, and he is very instantly you can make a friendship with him because he is very talkative as well as we can really have a lot of discussions with him with ease. So that, and top of that, he is a Bangalorean. So his parents were stayed in Bangalore. So that is why we have instant connection with him. And it is indeed wonderful to have you, Chris, here. And I welcome you to deliver your talk. Please.
Thank you very much, Professor Kulkarni, Anil, and dear guests and participants. Can everybody hear me fine? Okay. And I may move around, so I've asked for the microphone to be active even if I'm away from the dais. It's still working, right? Okay. Thank you. So again, wonderful to be here and address some of the remarks. Thinking about an audience that may be slightly broader in your interests and background, because I know several of the MSRMIS students are also here in public policy and economics. So not everybody here is a glaciologist or working solely on the mountain cryosphere questions, which wonderful to see all of the students who are doing that with Professor Kulkarni. But I want to give a slightly broader topic. And in fact, I'm not a cryosphere person by training. I'm a hydrologist by training, but even the hydrologists, careful. Even the hydrologists will say, but you've gone into water management. Now you're thinking about transboundary. That's not a hydrology question. Partly my point and my request and encouragement to all of the students is, do think about the links of your work, your scientific research and investigation with some other fields that are nearby and close enough where you can understand that and they can understand you. So let's not stay in our disciplinary home only. Let's also think about something which is inter and multidisciplinary. I'll come to the question of transdisciplinary, which is even a slightly different or a broader conception of that. So I did want to refer briefly to the mountain water towers concept. This is something to actually bring mountain water issues into a more public kind of a consciousness. So Professor Jayanta Bandyopadhyay, who some of you may know, is an eminent scientist who's been working in this field. And in 1996, he drafted this paper that's called Water Towers of the World, published in Geneva, Switzerland, in which he said that most of the large river systems of the world have mountain sources of water. Not all of them are cryosphere or snow and ice or glacier dominated, but mountains themselves form the headwaters. And so the relationship between the upstream and the downstream really has to be taken quite seriously. He gave some estimates of what sources of water were dependent on mountains, up to 80% by volume. And of course, when you think more about ecosystem services, and I know some of you are focusing in that area of your research, it becomes even more important. It's not only the physical flows of the water, it's the whole ecosystems associated with that, and also water quality also has to be concerned. So further work was done in this area by my colleague, for instance, Daniele Viviroli. We're working on a paper actually right now on some of these questions. Others, Walter Emerzil, and many others have been focusing on this mountain water towers kind of question. Let me refer briefly to the CMOD, which is the International Center for Integrated Mountain Development. And Professor Kulkarni and I, along with many others, were involved in putting up this report, the Hindu Kush Himalaya Assessment Project, HIMAP. And so we were in Kathmandu for some consultations and so forth. He led the cryosphere chapter, I led the water chapter, and you can see where some of the scientific work starts coming together between cryosphere, water, and mountains. Similarly, and when I was preparing the remarks to come here, he said our group focuses mostly in the Himalayan region, so why don't you speak about some of the other mountain regions? And so though I've done work in the Himalayas myself, and continue, for instance, with my student here, Teja Shirsat. So she's also both from this lab and also now studying there. Let me address some of the remarks to give you a perspective and a picture from outside the Himalayas, though some of the work we're doing is in Himalayan regions. So Appalachian Mountains, which you may know, and Andes region. And there are others working in this water towers concept in Andes, for instance, Condesan, or relating between Allegheny Plateau, Appalachian Mountains, and the downstream Chesapeake Bay, as an example. So all three of these images are on the same scale. The reason Andes Mountains is flipped from one side to the is not to suggest that that's the actual orientation of it, but to show you what a geographical extent it covers from north of the equator almost to the Antarctic polar region, right? And so you have a very large latitudinal gradient for the Andes that you would have either compared to the Appalachian Mountains or to the Hindu Kush Himalaya. So Hindu Kush Himalaya, of course, is extremely important for water resources in the region and also important from a population perspective. If you put a population area projection, these maps would look very different because, of course, the HKH region, Hindu Kush Himalaya region, with all of the very heavy population centers, not only in India, but in Pakistan, Nepal, but also north of it into China and so forth, will totally dominate the map if we were looking at this from a population projection perspective. But I just wanted to give you a sense for the spatial area and the spatial coverage. So what are some of the major rivers and what kinds of discharge and so forth can we expect coming out of that? I've made the comment that the mountains are important for orographic processes, capturing the atmospheric moisture, converting that into precipitation, whether that's rainfall or in the high mountains in the cryosphere, that's snow, and conversion into ice and into glaciers. But you can see the different river systems which are critically important. Andes, if you actually take out the Amazon River, and Amazon River actually is a river of its entirely own category in the world. It's got by far the largest discharge. You can see 1/4 kilometer of water per second is flowing in the cubic kilometer of water is flowing. It's a mighty river system. And in fact, if you add up all the other rivers on this chart, it won't come up to the level of the Andes River. So I mean the Amazon River. So these are critically important rivers that you can see get generated from that. You know, actually, I am sorry to say that this is my old PowerPoint. And somehow I didn't come up with the new one with the edits, but let's go ahead anyhow, because I will make some points here that are important. And then when we share the version, in case you'd like to distribute it among them, I'll make sure you have the latest version, because I've gone in to do a little bit more analysis of that to look at the dependence of that. So let's start speaking about the Andes kind of context. And so with my colleague at the Center for Global Change, Sebastián Becuña, in the Catholic University in Chile, who's a scientist working on mountain water towers in the Andean context, the big questions associated with Andes water generation in the water towers is the downstream use in hydropower. Why? Because countries like Chile, even Brazil, and other countries of the South America, which are dependent on the rivers flowing from Andes, are very heavily hydropower dependent. And so the total share of the country's generation of electrical power is very heavily dominated by hydropower. This is different from the other regions, for instance, the Hindu-Kush-Himalaya region or the Appalachian region, which have thermal power sources, which have other power sources, and including renewables, which are coming up, non-hydro renewables. But today, Latin America, and especially the Andean rivers, still are very heavily reliant on hydropower. So immediately, the flows generated, the timing of those flows, also hazards associated with those flows, not is the water available or not for generation, but what is the hazard, the flood, the glacial lake outburst floods, and other kinds of risks which are associated with hydropower development in the mountains are critically important. So Chile has some very interesting dynamics associated with what share of the total energy mix is generated by hydropower. You can see that there are some different inflection points, which are public policy questions. This isn't just sort of some natural progression that hydropower water is available in the rivers, therefore we will generate or we won't generate, but these are decisions which are made at the national level to take certain kinds of advantage of those water sources which are available in the mountain water towers for downstream hydropower generation. So you can see on the west coast side of the Andes, which are running parallel to the Pacific Ocean, they're very short flow rivers going immediately from the high mountains of 6,000 meters, 5,000 meters of the peaks of the mountains with cryosphere ice, especially in the southern part, because the southern hemisphere latitudes become very important in dominating. So you can have glacier cover in the southern part, even at 2,000 meters and 3,000 meters above meters above mean sea level, you can have glaciers. Whereas in our region here, of course, you have to go 5,000 meters plus, and then you'll start finding the glaciers, right? So these rivers are critically important, and they have a very short run from the crest of the mountain all the way to the sea, will hardly be 150, 200 kilometers. So this is very different from our rivers, which have a long flow. They get generated up in the high mountains, and by the time it reaches the mouth of the West Bengal in Ganga, for instance, or Brahmaputra, Meghna river system, these can be hundreds and thousands of kilometers, whereas these ones are just measured in a few dozens or tens or hundreds of kilometers. So you can start seeing the river systems in Chile, which are critically dependent on the mountain water tower system. So lots of work going on in terms of what are the climate change impacts on the glacier-sourced rivers, but also the snow-dependent snowfields. So there's no glaciers in some of the mid-elevation mountains, and further north, closer to the equator. Keep in mind, this is southern hemisphere. So closer to the equator, further north, there won't be any glaciers, but there'll still be snowfall in winters, and then that melt and snowpack will dominate the flow system. So how much is the water available? What is the timing of that water? And also, what are the risks of that high flow or even low flow periods coming down? So then these also start becoming local projects. Don't think about this only as the Ministry of Planning or the Ministry of Energy and Ministry of Water Resources planning for hydropower development in this particular region. Think about the local communities and the areas where these projects would be implemented and what kinds of debates are going on, because most of times the power is generated and it's evacuated via the grid to some urban demand source, and then the local communities won't benefit either from the hydropower or from the storage, which might give some irrigation and local benefits because now you can do some control of the rivers. And so there's a big opposition movement in southern Chile, for instance, which is called this Patagonia sin represas, which basically means Patagonia without dams, no dams. So this is kind of an appeal to that. So these kinds of discussions and debates have been going on quite extensively. But what I wanted to show you was the risk of low flow periods when you have an installed hydropower capacity if the mountain water towers, because of drought cycles, or there's a process of deglaciation, which I will also speak about briefly next, that you have very low flow periods. So what is your ability then in an integrated energy matrix to be able to actually generate power supply if, for different reasons of lack of water availability or change of timing of the flow signal? And we'll see some of the hydrographs as they come out in this process. So for instance, here is this Upper Maipo River I was involved in the project with my colleague, Professor Sebastian Vicuña, to do a whole Maipo River adaptation plan. So this gets back to mountain water towers and the adaptation, which is in my title of the talk, which hopefully you took a note of. What you can start seeing is the simulated flows going from the black flow sequence over the course of the year. And keep in mind that January, day one, is in the middle of summers, and July is middle of winters because this is Southern Hemisphere. And so what you can start seeing is the melt period after the winters, which is into the spring, which here is the months of September and October. Now they're having their spring snow melt because this is coming out of the winter period and so forth. And you can see that the peak of the flow in the black historical hydrograph. So any student of hydrology 101, the basic hydrology, would say the total quantum of water available from the mountain water tower generated is the area under the curve. All you have to do is multiply the flow rates by the time, and you will basically get total flow, and you'll get volume coming out, right? And so we can see that under future projections of climate change, according to the different climate scenarios that are being considered in this model, that the hydrograph is getting attenuated. There's actually less water being generated from the mountain water towers coming down to, in this case, the hydropower. And not only that, they have recreation and other kinds of ecosystem services below. Because the water runs through the turbines, it may still become available downstream for other types of purposes and so forth. But what you can start seeing also is a very modest shift going earlier in the season, and some differences in what is their winter season precipitation. So now you start seeing a change in the total hydrograph, but you also start seeing changes of the seasonality and unpredictability of the flows compared to the historical. So let's think a little bit about downstream use as being in hydropower, which is one of the key assets, because mountains generate not just water, but have elevation associated with that water. And again, students in very basic understanding of the hydropower is there's two main features of the flow in the river that you need to consider, which is flow and head. So rivers in the mountains should have both of those, right? You have not only water available because of snowmelt processes or precipitation runoff processes or monsoon processes, which are happening in the Himalayan region right now, but you will also have head available, which is a difference in elevation. So you can release the water from the reservoir and run it through the penstock and the turbines, which we saw in the last slides, or do inter-basin transfers and release it through a tunnel into the next valley and capture that head difference. And that's basically the generation that would come out of these river systems. So again, looking at these different contexts going through here in this Chile case, was how do you bring the different users and those impacted by adaptation? So the one slide which actually we did miss, and let me just touch on this here, is there are at least three main attributes of climate impacts that when we try to understand it from an adaptation perspective need to be addressed. So one is the temperature, and we understand in all of the model predictions and the historical record has shown that there is a monotonic increase of temperature. Year in, year out, we're just increasing the temperature. We may have 1 year which is slightly cooler than last year, but certainly over the period of time, there's no dispute anywhere in the historical or projected record that temperatures are not increasing. The dispute is not there. So temperatures are clearly increasing. That has impact on both precipitation phase. There's a change from snowfall to rainfall. There's also a change in the timing of that as a result of the precipitation cycle, because land and atmosphere warming processes change. Land atmosphere transfers of water, for instance, the Indian monsoon, South Asian monsoon, may change also as a result of climate impacts. The ability of mountains to capture that precipitation because of the changed circulation patterns, not at the global circulation, but at the mesoscale circulation, will change. The second one is the precipitation changes themselves. Different regions are experiencing different shifts in the precipitation quantum that is coming, whether that's in a solid phase or a liquid phase. Actual quantum is changing. A warmer atmosphere holds more moisture. The potential is there for greater precipitation. Certain arid regions, according to the circulation patterns, don't actually have the ability to capture an increased precipitation coming out of more moist atmosphere because the circulation is taking that moisture in a different direction. Where we are in the east coast of the United States, we actually are getting increased precipitation, both in total quantum, but also in the intensity of that precipitation. So we're having more storms, and they are more intense storms. Added to that, and we'll come to this slide a little bit for the Chile case, is a new understanding of atmospheric circulation called the atmospheric rivers. And that is concentrated jets of moisture which are piercing through a general frontal system, when you look at it from a climatological perspective, into narrow concentrated jets. And you can now do moisture tracking through satellite means and show that it is actually an atmospheric river. This is not a river flowing on the land. This is a river flowing in the atmosphere. And so when that actually comes, you can have very pronounced flood impacts and all kinds of things. So this is where hurricane impacts, tropical storm impacts, atmospheric river impacts on the land can be a feature of the climate. The third one is where we mediate between the human use and the response of things like land use, of our ability to develop infrastructure to address questions of increasing temperature and precipitation, climate change impact. Not simply that human societies and human infrastructures and human settlements and human systems are receiving the impacts of climate change, but because we are also driving that climate cycle, both through emissions of carbon and change circulation patterns. But because we are modifying land use, because we are building infrastructure of a certain kind, the actual river system will respond differently than if it didn't have that kind of thing. So I'm sorry, that was the slide, which is more the sort of conceptual level, which I wanted to get to you so that we start talking about, okay, what is the downstream impact? Let's look at hydropower. Let's look at some of the other things. So again, I'm sorry, that slide is on my newer version, which I somehow didn't get copied into today's presentation. So here is, and keep in mind, to the east side in the purple are the high mountains. In this part of the Andes range, the maximum elevations don't get quite to 6,000 meters, but get to 5,500, 5,800 meters. And the whole river system flows basically to the west. And the gray area in the middle is the city of Santiago, which is the capital of Chile. And then the green areas, all the irrigation systems downstream. So again, here is the trade-off between upstream hydropower generation and downstream irrigation. And the trade-off primarily is the timing, because if the reservoirs in the high mountains are holding the water when irrigation requires it according to the summer planting season and when the crop evapotranspiration requires the irrigation, then the release schedule will be different as compared to if the reservoirs are operated for hydropower purposes, which are requiring on a diurnal cycle, afternoon and evening, the city is requiring the power. So the power generators are running the rivers not to meet the convenience of the farmers, but to meet the power generation schedule and so forth. So you have to understand how those things all together. Similarly, because Chile has a long mining history for copper particularly, but other types of metal purposes. Now there's a whole new lithium mining, not in this basin, but in the northern part. It becomes important to understand what ability humans actually have to do the infrastructure changes. So is there a massive tunneling network? And here, this basin of the headwaters of the Maipo actually has significant copper mines. And so the copper mining industry also is the same one that is developing the tunneling that is allowing for the intrabasin transfers of the hydropower. So let's just say, absent the mining sector, absent the mining industry, the tunneling capacity to actually build those tunnels is less. And so therefore the planners who are planning the hydropower now are starting to think that they have a different capacity to make these transfers according to where the yellow lines are going as tunnels in between the thing. This is just the same map, but showing the different kinds of things. Okay, so then in this particular basin also, there was a new increase in total capacity. So in 1991, they put new power stations online, and you're starting to understand what the different capacity for generation on an annual basis is. What becomes interesting is looking at the capacity of these different plants to generate over time. This is that same Julian day, cycle. Keep in mind, January is middle of summers. The middle of winters is coming in July. By the time you get to August, September, now it's the spring snowmelt season, which is when the primary generation takes place. We've seen this figure before, and also trying to then understand what is the total peaks of the hydrograph, but also what is the shift over time. And then, of course, looking at the long-term projections over time, in this case, only out to mid-century, but you can see that all of the figures show a decrease in the total quantum of water available for hydropower generation. So now you have to have not simply how does the plant operate, but what is the sectoral planning for considering how these kinds of things work. So again, this interactions among the water, energy, and food, where the energy demands actually drive the release schedules. Usually we don't think that the water flowing is simply a response to some operators, but when you have a heavily built up river system, of course the flow is anthropogenic flows. It has nothing to do with the way the river would normally otherwise be flowing. Agriculture actually becomes one of the sort of, it's a residual user, which means they'll take the water whenever they get it from the hydropower sector, because that has a higher economic kind of a value. But then the planning initiative that went through where all the stakeholders came together, including the authorities, local communities, but also the NGO groups who were doing more ecological preservation, let's say the environmental lobby, the ones who were keeping up the river quality and so forth, all came down to some decisions to try to do that. Finally, no ultimate solutions where everybody was pleased with the outcome, but there were some accommodations made to basically accept that. So that's the central southern case. Chile is, again, a country with 6,000 kilometers long and 250 kilometers wide. It's a narrow strip of land all the way along, and it goes from very far southern down to 60 degrees south latitude, and its northernmost point, I think, is 18 degrees south latitude, south of the equator. So it has a huge 6,000 kilometer coastline and different river systems, and you can see that the latitudinal gradient is very important. Let's go here to the north of the Andes, and you can see in the background the outline, which is Central America, Mexico, and Panama. And then this is on basically the IPCC Climate Atlas. You can see the northwestern South America climate region. You can see the Caribbean's climate region, and you can see the northern South America climate region. And all of these three are intersecting at this point over here. And the slide which I showed you on the cover slide for the talk, which showed the mountains behind it and the river flowing through, is this northernmost point, which is called the Sierra Nevada Santa Marta. It means the snow mountains of Santa Marta. It's a very interesting mountain system. It's the northernmost point of the Andes. It reaches just short of 6,000 meters. It's 5,980 meters. So you must have seen that movie where if you could just build up your hills a few more meters, you could get your town on the map because it reaches 1,000 meters. There's some film from Scotland or something. Maybe yeah. I'm digressing a little bit. They're reaching just 6,000 meters, so forth. And the Caribbean Sea, it's the highest coastal mountain in the world, which means 6,000 meters to sea level in a trajectory of just 150 kilometers. So it's a very steep mountain system, but that mountain also sheds water to the east, to the west, to the south. What's interesting in this is it's actually at the intersection of three different climatic regions, which means the uncertainty then plays with what kinds of future projections will you look at? Will you place this location in the Caribbean region, which has its own annual and seasonal cycles? Will you place it in the northwestern South America region, which has its own Pacific Ocean-dominated cycles? Or will you do it the other one, which has not only the Atlantic from the ocean, but it has the Amazon, which has its own climatic drivers and, again, moisture signals and so forth. There's been some very interesting isotopic work to understand origins of rainfall occurring in this mountain region. And in certain storms, the water is indeed coming from the Pacific. In certain storms, the water is indeed coming from the Caribbean. In certain storms, the water is indeed coming from the Atlantic via the Amazon. So it's kind of an interesting area which we'd like to do a little bit more focus on. So here's where we've actually done some of this interactive modeling with different kinds of stakeholders. I won't go through all of this, simply to show that we have a whole range of government, non-government producers, meaning local growers and other kinds of thing, some small subsistence, some agribusiness kinds of growers, and the towns and so forth. Interactive, workshops where we're actually, getting different stakeholders. And this is a young guy from the agriculture ministry, basically their extension department, generating these kinds of maps over here, and not simply here are your outputs and outcomes of water scarcity over future scenarios of climate change, but critically, you'd please tell us what kinds of decisions your own users group might be able to put. Would you go in for higher efficiency irrigation? Okay, it may be costly. How much would there be that cost? So you're doing an interactive way to look at adoption of water and land management practices, which will then come back and influence the way the river basin responds not to the climate signal only, but to the water management decisions, the infrastructure, and so forth. So we've done quite some kinds of interaction. This is trying to understand how the changes. I had taken all this out because though it's in Spanish, you know, I didn't really want to cover all of that. But here we actually have the water evaluation and planning WEEP model, which some of you are using currently. It's a water resources model. It has some hydrologic, you know, response capabilities, but really it's a water resource planning tool. But it's a good and a transparent mechanism to actually be able to sit with stakeholders and say, okay, so you're from the irrigation department, so your changed irrigation schedule, or you're from the farmers group, you will plant some different crops. What are the implications of those over the time? So this is what we basically do with what's called serious games. We try to gamify it, right? So the one is, yes, make it an interactive game. So people are getting interested, yeah, gaming. We're all interested in kind of, you know, some of that, but it's serious because what we're trying to do is get some shared outputs or find out where the difference points are. No. Some groups will definitely be different, and you'll never understand that if you're just sitting without actually putting your numbers and your data into the system. So the gamification of this is something that is quite important. So we did that energy use index. We did a water use index to actually understand these kinds of things and brought it back to the users to say, okay, how would you like to go about this now, right? And so some of this is the transdisciplinary part. This involves academic and scientific research. It's built in the model. It's built into trying to understand the climate signal. It's built into even the social science part of it about who are the users, what are their different response levels, are they functioning from an economic rationality perspective, are they functioning from more of a preserve my livelihood and preserve my thing, which are not necessarily economic decisions. But then you're finally putting it into discussion spaces like this, right? Which means we're getting outside of the academies, we're getting outside of the disciplines. So we're going beyond the disciplines. So this is the transdisciplinary. And the talk I just gave a couple of days ago in South Africa was in the pursuit of the Sustainable Development Goals, the SDGs. We often do a multidisciplinary approach, and we often even do an interdisciplinary approach. So the multidisciplines is the hydrologists and the economists sitting down and saying, please do your work in relation to my data set or whatever, but then you'll go back to your corner and do your work. I'll sit in my corner and do my work. We're doing multidisciplinary work. But the interdisciplinary is where we'll say, hey, you please take my data set and you do something with it, or send your student into my lab and we'll do some work on. So this is now we're doing interdisciplinary work, but we're still entirely within the research, or we're still entirely within the academics, right? We haven't yet gone to the users. We haven't yet gone to the decision makers. We haven't yet gone to the farmers. We haven't yet gone to the society at large. When we do that, we have to put aside some of our disciplinary biases. No. I insist on an R-squared value above 0.85, otherwise the model is useless. No. Now you have to start discussing the decision makers. They don't know what all those terminologies mean, right? And so this is where you start doing some of that kind of work. A lot of it is poring over the maps or other kinds of generated output. Those serious games outputs can go in this map. People look at it, say, no, that doesn't make sense. How can we change that? How can we modify that? Okay, so here's a little bit of some, this is the part that I should have brought through. So let me just speak with you briefly about the Appalachian Mountains, which run from the southeastern United States all the way up into Canada. And you can see its trajectory that is longer from north to south than the Himalayas are from east to west. So think about a piece of land, if you will, that runs from Afghanistan through Pakistan, through India, through Nepal, through eastern India, through into China, right? That's how long this Appalachian mountain chain extends from north to south. It's relatively large. It's not as long as the Andes, but it's certainly as big in area as the Himalayan region. So it's a large area. Rivers are less important because they don't generate as much flow. They have a shorter run. But here, what we're interested in is not the ability of the rivers. I mentioned it's a relatively water abundant system. This is an ecosystem that actually has adequate water for most of the forest growth and most of the ecosystem processes. It's not water constrained. It's not an arid region or a semi-arid region. It's a water abundant region. But here, the rivers are implicated very seriously with sediment transport and delivery of the sediments to the downstream estuary and the river bays. And therefore, the water pollution, the water quality impairment, and also then the ecological process and fisheries. There's a very important crabs and fish and shellfish and which is in the downstream, right? So think here not so much about the mountain water towers generating water for the downstream, which of course they do, but the water becomes the conduit, becomes the mechanism for the transport of the sediments, and with the sediments go the nutrients, right? Especially nitrogen. And I am sorry, indeed, I brought up several figures here to show about nitrogen surplus is a big challenge because nitrogen is actually imported from outside. These are not local sources of nitrogen. We're not growing the crops, which are then being used to produce the compost, which are then used to fertilize the fields. We're actually bringing the nitrogen from outside, right? So you have to do a mass balance of the nutrients to actually understand what is happening in that watershed. And the watershed area downstream is very significantly impacted by the nutrients. And so the big questions in the Appalachian Mountains, Allegheny Plateau, Susquehanna River, and Chesapeake Bay, which is that same chain of river systems and causality that we're looking at in the Andes, that case, or that you may be looking at for the Himalayan case there, is about river flows and nutrients and sediment. Okay, so think about it, it's a slightly different concept. We're not only interested in the water volume and the quantum, but actually the water quality process associated with that. So again, there's a whole process of the scientific investigation, and what is the nutrient dynamics, and how much is eutrophication taking place, and what is the algae growth leading to oxygen depletion? I mean, all the scientific questions are there, and we're working on those, if not in my lab itself, but the point is there's a multidisciplinary and interdisciplinary group working on those challenges. But what is the objective of that? It's actually to try to come up with a nutrient budget. Same way as we might have a water budget to say, this is the inflow and the outflow minus the change in storage. Here we're trying to do a nutrient budget. How much is the nitrogen and how much is the excess nitrogen because the imports are coming from fertilizers? And there's some atmospheric deposition, not much, but the dust actually can bring in enough. Phosphorus is a different nutrient, which you also are looking at. Nitrogen is very heavily imported. Fertilizers are generated and produced outside. That fertilizer is applied inside the basin, and then the mountain tower, water tower, river flows are bringing it down to the bay. Phosphorus is a slightly different case where the phosphorus budget has been managed actually much better. And now we're at the level where we're starting to see the atmospheric deposition of phosphorus coming in the dust, blowing in from outside and settling in the river basin. And that is, of course, causing its own source downstream. So again, so sorry that the slides were missing and so forth. Let me shift over to speaking very briefly, which gives you an example of the kind of approaches that we're doing to link up and tie up our international collaboration in that case of the country of Colombia, that, for instance, could give an idea of what we might be able to do between Penn State and IISc, because our two institutions have a high-level tie-up. Our vice rectors and vice chancellors and everybody has signed the highest levels of memorandum of understanding. We are collaborating in other fields, and I think my visit with you is the first visit in the climate area and public policy area. So maybe we can think of some ways to do that. So here are some studies that we have done as an example in the Andes, focusing on what's called the paramos, which are the high elevation peatlands. These are areas that after the Pleistocene era have been deglaciated. So don't think of today's climate change impacts on deglaciation. Areas have been deglaciating for thousands of years. And those high elevation areas are very productive ecologically and are generating lots of organic matter. And that is stored in peat soils. So anoxic conditions lead to a lack of decay of the organic matter. And then you actually get a buildup of volcanic water storage and water holding capacity that, as climate is changing and drying and temperatures are changing, now they are subject to a shift into a different ecological regime where we are losing some of the organic matter and potentially the ability to store the soil. So some of Tejal's work, where she has gone last year to do some interesting work with the WEEP model applications in this river basin system, was to understand how much of the flows coming out of these high elevation mountain water towers are coming down and become available for different ecosystem purposes and human purposes and so forth. Here's the team of people who are working on this particular one. And this has nothing to do with the mountain water towers. Now I'm starting to talk about general collaborations around water, energy, and sort of climatic processes research with this country of Colombia. Off-grid is an island energy system. Food security here is a very arid region. They're doing solar irrigation, pumping, and so forth. So these are all topics that can generally be brought up and so forth. And then the last one is the project I was working on of those four between the two partner organizations, Penn State and the Columbia partners, was that set of serious games from the mountain water tower, which is just on the Caribbean coast, which I remarked on. So I presented some of those results, but this is the project under which it was brought up. I actually will stop here and take any kinds of questions and comments. And maybe while that is going on, I will ask maybe whether Mr. Srinivasan in the back or my good colleague could go into Professor Kulkarni's office and just bring my computer bag. And in the meanwhile, while you're asking the questions, I will put the real PowerPoint up. Again, I'm so sorry. I thought I had the latest version. Sometimes these things happen. I'll just attribute it to sleeping 4 nights on the plane out of the last 5. So 1 night I had in the hotel and 4 nights I had on the airplane. And so, yeah, I'm not thinking quite straight, but I will get the right PowerPoint up for you, I promise. Okay, so let's take some questions and answers. And then I hope by 4:30 we'll be completely done. So please, any kinds of questions and comments. Someone in the back there, if you could also identify yourself, or at least where are you coming from, or do you have a specific discipline or department where you're coming from? Yeah. Yeah. Okay, so if I got the question, is Chile's hydropower development, is it private development or is it state controlled, and what is the discussions around that, right? Okay, so some of you may know very briefly, and I won't go into all of this in details. In the 1970s, Salvador Allende, who was a socialist president of Chile, was deposed in a coup, and he was executed and killed and replaced by military general Pinochet. Okay, and the U.S. CIA played a role in all of that. It was a dark history of Chile's history. But what that has resulted in is Chile is the country, arguably, maybe aside from Singapore, with the highest degree of privatization of absolutely everything. Everything in Chile is privatized. Everything. The trains are privatized. The buses are privatized. The hydropower is privatized. The mines. Everything is privatized in Chile. Okay, so basically, Chile's development is 100% private development of the hydropower. Now, that doesn't mean that the state won't play a regulatory role, that the size, the location, or the power purchase contract, all that would have to have some degree of oversight from the state. But yes, the answer is it's entirely private development. And then maybe there's a follow-up question, and I'm going to be doing parallel processing, which is to get my computer and get my talk while we're chatting. Let's see how well I do this, because
so on the science front, you can show, maybe I missed it, any land use, land cover maps in Chile. Has that changed dramatically over the past 50 years there?
It has to an extent, in the degree to which Chile, like many countries, is going through rapid growth and the city is expanding. And so in that particular basin, the city's footprint expanding onto the mostly irrigation areas. That's the thing, because both of these are in the lowlands. So the city's not growing into the catchments and into the hydropower areas. So if you look at it, it's a very different type of river basin system. Mostly, you would think, particularly from the Himalayan perspective, the lowlands are somewhat drier and have less forest cover, and the highlands actually have more, I mean, up to the tree line. Whereas in Chile, it's completely different. All the greenery is in the lowlands, and the mountains are entirely bare. They look like, let's say, Trans-Himalaya, like Ladakh or something like that. So yeah, please, any other questions? And my slides are coming up, and I'll just not go through the talk again, but I'll show the critical few slides which were missing. And again, so sorry that's usually not the way we have it. So any other questions about that mountain water towers concept, or what is the actual climate impacts that we are adapting to, or any other questions which you may have? So Pradeep, can you just put this, if you can put this, it's at 4, if I remember my, don't worry about the changing the saves, changing the filing, saving changes. It's fine. Actually, what I'd like to do is just show those Appalachian, Allegheny, Chesapeake Bay, because I think you could be quite interested in that. It is similar to maybe, let's say, Eastern Himalayas, in the sense that there's a water abundant system. Mountains are actually generating river flows, but it's not the quantum of water, it's the flood risk. And it's the water quality that we're interested in, as much as a water balance to say that there's adequate water for meeting the needs, which is more the Western Himalayas case and more of the Andes case which I presented.
Sure.
So let's just go. Yeah, it's this last one which would have been saved. Yeah, yeah, please. Just open it from the screen and I'll give you well, just don't save. This one, don't save. And is this the new one? And then open this one again. Yeah, okay, and it opened on the right slide. Look at this. Yeah. Okay, I think these are the ones that I was interested in. Okay, so what you can see here, again, sorry, let's go through these ones. Yeah, okay, briefly. So the eastern seaboard of the United States, the Atlantic Ocean, Appalachian Mountains here in the southern part, and go all the way up to the north part, Canada. Again, north to south, roughly the same distance as Himalayas, east to west. So the area is kind of the same. And here are the river systems which are all coming down. And this water body is called the Chesapeake Bay. Okay, very important. It's an intercontinental area, and major rivers that are coming down are from our state of Pennsylvania. And so the Appalachian Mountains in the northeastern part of our state are the water towers for the Susquehanna River, which is flowing down. And again, that's where I've mentioned the big challenge of these river systems is not so much water scarcity. There's abundant water for the purposes, but it's the ecosystem water quality and it's the human impacts on nutrients and sediment, which is coming down and impairing the water quality of the bay. And you can see some of the sediment plumes coming down. A high storm event will cause this kind of visible water quality from satellite imagery. And of course, there's all the measurements which are going into, suspended solids loads, but also nutrient water quality. And these are the kinds of things which are down. This is a very important estuary, both for ecological purposes, because any estuary or bay which is productive in that sense ecologically also has the potential to be productive from an economic point of view of the fisheries and crabs and shellfish and all kinds of things. So this is the system that we're working on. And I think I've got here some of the adaptation challenges that we're focusing on. As different from flood and drought, it's really flood and flood hazard, right? Human settlements, but also ecosystem processing in the river channel, which is subject to very significant flood events. Sediment is a big land-based nutrients coming from crop agriculture and livestock. It is also rapidly urbanizing, which means that the urban waste, which is all of the sewage effluents and all that, is still coming down. That is better managed. These are what are called point sources. You can go into the city of Washington, D.C. or Baltimore, these 100 million population plus, and say, all of your sewage treatment plants have to meet the following characteristics. And there's 6 or 10 treatment plants, and the inspectors can come and they can actually crack down on it. Okay, so that part has mostly been dealt with, right? There's still some question about what happens to the biosolids afterwards. I mean, all those questions are still there. But when you talk about nutrient loading coming to the bay, it's the non-point source, which is mostly crop agriculture and livestock. Pennsylvania is the state where we are. 50% of the cover of the state is forest. Of the 50% of this forest, this may be the question that the gentleman was asking, is 75% of it is private land. So you can already see that a very significant institution is individual landowners. These aren't corporations who have bought big forest areas to do the plantation forests. These are farmers, basically, who part of their farm is in forests, right? And don't think of small farmers, but in the US context, they are relatively smaller farmers. A farmer may have 100 acres or 200 acres. So that's big by many standards, but it's not huge by some other standards. And let's say half of that land will also be in forest. So this part is entirely forested and the rest is all agriculture. No, it's a patchwork. But the decision makers who have to decide about to adopt certain kinds of practices to adapt to the climate change are many small users, right? Individuals. Nobody's going to come and say, you will adapt to climate change this way. But of course, the federal government, which is our central government, state, even local governments have their adaptation plans. And there's a very robust and strong, as there is in India, which there is not in many places in Latin America, where I work, a strong civil society. NGO groups who also take an interest in it and bring science to the table and say, we have done some analysis, or we have taken this academic research results, and this is what we feel should be the outcomes of it. So the civil society, the NGOs are an important actor also in this one. Let me mention briefly, this has nothing to do with the water towers, but you might be interested, is there's actually a quite advanced process of land subsidence going on. These are marine sediments, unconsolidated sediments, through different processes of isostatic shift, but also groundwater pumping. These vast areas of the eastern seaboard of the United States, including that entire Chesapeake Bay, are sinking. Regardless of whether the human impact is there, although groundwater pumping and dewatering of the aquifers plays some role in the acceleration of subsidence. And these are processes that are happening in other places of the world as well. With China, big city Shanghai and everything are also subsiding, right? Again, nothing to do with the water towers argument, but let's look at this in the broader ecological context. So this is what we're trying to respond to. These are the figures that I wanted to bring your attention. Don't worry so much about the other ones. I mean, they're all quite interesting, but this square at the bottom, which is the Susquehanna River, which is that large one that generates that sediment plume, that comes down into the top of the Chesapeake Bay. And here we are seeing some very important changes to say that now keep in mind, this isn't nitrogen level, this is nitrogen surplus. Okay, so though we're getting better in the surplus, we still have a huge surplus. Okay, and you can see how it's broken down into different forests and different kinds of land uses. So think about climate change going on at the same time as the human processing for changing land use, farmers adopting how much, I'll let some more of those acres go into the forest cover because I don't have the ability to farm them, or the crops are not paying the benefits, the profit levels aren't high enough, or my kids are not taking on the farm yet. I'm getting 60, 70-year-olds plus, how can I keep farming the farm? You know, so all those processes are going on at the same time. But what is also quite interesting is some really different shift going on over time of how much is the nitrogen surplus compared to how much is the nitrogen loading. Loading is what we were able to somehow control to put on. Not that we as the government, any decision makers say, you will only put that much surplus, but farmers are adopting under different kinds of things. And so it is actually taking a process of the nitrogen surplus is coming down. I think these are some positive signs that we're starting to look at. Okay, the last thing which I would say, partly because many of these processes are tied into energy. Not only because I take the water, energy, and food nexus approach at some points, but I think it is a strong climate adaptation process. Okay, what I mean by that is, if we only look at climate impacts in the water side, then we miss the opportunities from land planning, we miss the opportunities from energy planning, we miss the other opportunities that can also have a chance to give us the ability to respond to climate adaptation, which is. So that's the concept of this water and energy. And also, you make an energy decision, it may have an impact in the water and vice versa, right? Hydropower is a perfect example. We need water to generate the power, and according to how much power we have or demand, the water and so forth. But the Appalachians don't have much hydropower. There's a little bit of hydropower, small amount. In fact, when she first came, we were both saying, where's the hydropower? You should find hydropower. Well, there are one or two plants, but it's not very big. It's not much. The main source is natural gas. Okay, and it's extracted through a process called hydraulic fracking. You probably heard about the fracking. And the fracturing, of course, is a whole process from, subsurface geology that is beyond my understanding, but it's not my field of inquiry. But it requires a lot of water. You have to have hydraulic fluids to frack the underground thing to extract the gas. But then when you extract it, also you have contaminated water. And so now you start coming into a double, problem that you're extracting carbon, you're feeding that into power generation. Luckily, it's substituting coal. So coal has even more carbon emissions per kilowatt hour of electricity generated. Natural gas is only slightly better. I wish we could go into solar and wind and tidal or other non-carbon sources, but for the time being, at least this part of the country and this part of the economy is into the gas part, but there's a strong water component of that because it's a hydraulic process, and there's also a wastewater fluid which comes out and so forth. Anyhow, that's what I sort of wanted to cover up in there, and now we're back to the Chile case. So again, so sorry about that. We'll do one thing here, and then I will just refer to some very interesting research that Tejal is taking up, and we'll have some chance to talk about it afterwards. I mentioned that we're doing this collaboration with Colombia, and that there is some scope to do some different kinds of work. Where did that slide go? Here, yeah. So again, application of the weak modeling tool to do interactive scenario planning with different stakeholders. These are the high elevation peatlands. So this is at an elevation of probably 3,600 meters. The higher elevations, keep in mind, this is almost equatorial. So you get vegetation at a very high level above sea level, even at well beyond 4,000 meters, plenty of vegetative cover. But you can see there are water towers, not because they're capturing orographic precipitation only, but because there's actually a storage mechanism there. So it is really not only a water tower, but it's a water tank also. It has a very strong storage and regulatory concept. But some interesting work that she and the other team members have done, looking at the applications for the city of Bogota, which is their capital. City population of 10 or 12 million people. It's not a small city. I mean, in Indian standards, maybe it's not so big. When you say in the United States, 12 million people, everybody goes, wow, that's like a huge population. But of course, all these people are requiring water and so forth. Analysis of the station data, really trying to get some, precipitation surfaces, developed out of that to see whether we can't do a better job of predicting what the flow is coming out. And this is a classic link node diagram of type of model, which basically doesn't predict the hydrology, but says, here's our current understanding of the hydrology. How will the actual infrastructures move the water from A to B? Will demand, because this is a treatment plant and distribution works, putting water into the city's pipeline distribution system, will it meet, and those kinds of things. And right, so there's some interesting work that's going on in this. This topic has gotten some interest. Amazon company, the actual sustainability division of Amazon, has given a small grant to do some work on sustainability planning. So we're starting to build up some of the different types of support under that. And then I would like to go into one other thing. And again, if we have questions around this, I'm sure Tejal will be happy to answer that. But how come I keep coming back here? Oh yeah, hang on. Here, let's go right here. And this is now slightly in the East Coast. I know I said we were working on the Andes and we're working on the Appalachians. So this is now the Cascades Pacific mountain system way on the West Coast. This is the state of California. This is the state of Oregon. This is the state of Washington. This is Canada and British Columbia. That's another mountain water tower system and so forth, and different systems. But actually the Columbia River, though it discharges here, the whole catchment is mostly in Canada and partly in the United States. But the point here also is that hydropower planning involves not only current infrastructure that we have, but the future potential for pumped hydro storage. So it's a water storage mechanism, but it's also an energy storage, right? Pumped hydro is currently the best batteries we have at large scale, right? We're trying to build different kinds of lithium batteries, trying to do compressed air storage of energy. But the best way we have is when power is surplus, use the power to pump the water uphill to the storage reservoir. And when it's in demand, run it back down. There's efficiency losses. You'll never capture all the energy. You're losing some energy because there's inefficiencies. And electromechanical, mostly inefficiency, just in your turbines and your pipes, and you're losing by friction and you're losing by. But you're able to capture and store the energy from day to night and from maybe not season to season, because these are not huge storage systems. You can't store a whole season of flow and then run it next season. I mean, that's too big of a thing. But I know parts of Northeast India, also in Sikkim and other places, are considering pumped hydro storage. And so these are also some of the ecosystem services. And you can see these are low head, high discharge, as against high head, low discharge, which is mostly what we think about with the small hydro plants high up in the mountains. But here, even if you have a fall of 10 meters in a river system, the Columbia is a huge river system. I don't know what the average flow, but it'll be larger than the PGM, I think. It'll be on that scale of tens of thousands of cubic meters per second average all year long. Imagine running that through your turbines, you get quite a good hydro generation. Okay. And then looking at climate change impacts, again, associated with total quantum of water available, changes over time in terms of when the flows become available versus you're no longer able to meet certain power purchase agreements. So think about these also in really in the economics and microeconomics perspective of saying, I'm a plant operator, I have some contractual requirement to deliver power to my buyer, which might be the city, which might be an irrigation district, which might be an industrial group. Now the water isn't coming out that I meet my contracts, right? So those are also the way in which I think we have to think about some of these things. And then integration of some of the pumped hydro. So Teja led the chapter, which we just submitted, I think, 2 second reviews, and then okay, can you cite some of these in slightly higher elevation areas where you would pump it up, and then when the demand requires, you can run it back down and down. You need pump storage kinds of things. And then briefly, we're going, starting on Sunday, up to Chandra Valley in the Chenab River Basin, where we'll do some work where much of that I think Deja has brought her expertise from here, so from ISC and the Procurement Lab, to really look at some of these. And now we're starting to address what are the uses and users, including in hydropower and small-scale irrigation. Are farmers planting potatoes under small drip and sprinkler irrigation systems? What do they make of the different timing? Is the water available to them? Some of the question about the ice stupas and different other sorts of things. So some of the high mountain adaptation mechanisms are actually within the mountains. So sometimes we think about adaptation mechanisms of what the mountains are doing, and the lowland has to adapt. So sure, the big irrigation within the systems and the big urban areas downstream will have to adapt. But within the mountains also, adaptation processes are going on. And so let's try to understand what those are in hydropower and other kinds of things. And so this is going to be one of those, and we have a small survey designed to try to actually capture what some of the users are doing. And I'll just leave it at this because this ends currently where some of the work that Dejal is leading in our lab. And because I just shifted to Pennsylvania 3 years ago, we have a very small lab. She was the first one. We have another one for Eastern Commodities. We have a postdoc coming on East River. And we have several other students who are attached to our lab group who are advisors or in the department, one from agricultural economics, one from the field of education. So we're building a nature transdisciplinary group. So let me end there and thank you all for your attention. So sorry again about myself.